The section's on 8.2, L'Hopital's rule. So let me go over the L'Hopital's rule. It says basically that we have a function of f of x and a function of g of x, and we're going to be given a limit similar to what we did in calculus AB. And then we have is x equals a, which is also a 0 right here. So we're saying that the limit as x approaches to 0 right there, you're going to have as f of x over g of x. Now in calculus AB, what we did was we actually did a UV and we did a quotient rule. We took the derivative of this right here, and then we most likely substituted numbers from there. Okay? So what we're doing for BC now is that we're going to try to do that, but we're going to have a problem, because if I actually substitute in 0 into the f of x and also g of x, most likely you're going to get a 0 over 0. And we cannot have a 0 over 0 because anything divided by 0 is undefined. So this is called an indeterminate form. So what we're going to do now is apply L'Hopital's. So L'Hopital says basically that if you have an f of a and you have g of a, what you're going to do is then if it comes out to 0, 0, you're going to take the first derivative. Okay? Now this is a little different format because the f of a right here is actually an individual equation, and g of a is also a different equation. We're not doing a UV and a quotient for this one. We're actually going to take the first derivative, just the f equation, which is the numerator, and then take just the derivative of the g of a, which is the denominator. Okay, so then from here, it should work out to a number right there. Now 0 is also a number, so you're okay if you have a 0. But anything divided by 0 can be a problem, because then that's an undefined. Now if it's still on this type of problem right here, if you try to do your L'Hopital's, and it still comes out to something over 0, or 0 over 0, then you're going to go to a second form, which we call it the stronger form. And the stronger form basically says that if you took the first derivative for both the a, f, and the g, and it still came out to 0, you're going to go second derivative. So you're going to do second derivative on the numerator, second derivative on the denominator, and again, this should work out now. Okay, so let's try an example. An example is when we have the limit as x approaches to 0 of square root of 1 plus x minus 1 all over x. So I probably want to change this square root into an exponent, right, to make it easy for us on the derivative. We're going to take it to the half power right there, and then the derivative says I bring the half down and I subtract 1 on the exponent. Derivative of negative 1, which is a constant, is 0, and then derivative of x is 1. So we're going to get something like this. Okay, now I'm going to substitute my 0 into this equation where x is. So 1 plus 0 is 1. 1 to any exponent, right, is 1. 1 to the half, 1 times half is half. Half over 1 is going to be basically half, so that's good. Okay, because that's a number right there, a real number. All right, let's try example number 2. So example number 2 says 1 minus cosine x all over x plus x squared. So again, we're going to take the L'Hopital's, we're going to take the derivative of the numerator, and then take the derivative of the denominator. So derivative 1, which is a constant, so that's 0. Derivative of negative cosine, right, is positive sine. Then derivative of x is 1. Derivative of x squared is 2x. So we have something like this. Okay, so now that was the application of the L'Hopital's. Now we're going to substitute in 0. So sine of 0 is 0, right, because sine does not own the x-axis right there. And then if we substitute 0 into this part right here, 2 times 0 is 0, but 1 plus 0 is 1, which is fine because you have a 0 over 1, which is equal to 0. So this is good because it's not an undefined right there. Okay, now let's try example 3. So example 3 looks similar to the previous example 1. All I did was I added on to this is the minus x over 2. Alright, so from here again, we're going to take this, make it into an exponent of half right there, bring down the half, and then we're going to take the subtract 1 on the exponent. This right here is the same thing as saying negative half x. So when we take the derivative of that, it becomes negative half, right? Derivative of x squared is 2x. So we have something like this right here. Oh, I'm sorry, this is the switching of the exponent right there. Okay, so then from here we do have the derivative. Okay, now from here I'm going to substitute in my 0. So 0, if I substitute this in, 1 plus 0 is 1. 1 to any exponent is 1. 1 times half is half. Half minus half is 0, which is fine so far in the numerator. But then if I substitute 0 in the denominator, we have a problem because now we have is 0 over 0. Okay, so obviously the L'Hopital's on the first part did not work, so we now have to go stronger. So stronger says I'm taking the second derivative. So from here, this spot right here, we're going to take the second derivative of the numerator, and we're going to take the second derivative of the denominator. So from here again, I bring the negative half down right here, I subtract 1 on the exponent, right? And then I get derivative of the negative half, which is gone because that's a constant. Derivative of 2x is 2, so we're going to look something like this right here. Okay, now I've done the second stronger form of L'Hopital's. Now I can substitute in 0 into that equation right there. I just simplified right there. That gives me negative 1/4 right there. Alright, so then from here I substitute in 0. 1 plus 0 is 1. 1 to any exponent, right, is 1. 1 times negative 1/4 is negative 1/4 divided by 2. And then from here, I believe I can multiply the reciprocal of that 2 because it's fraction over a fraction right there. So this is like saying 1 over 2 when I multiply the reciprocal. That gives me negative 1/8. So again, this is a real number, so this is fine right there. Okay, so that works out. So again, the first derivative, if you're doing this and it comes out to an undefined, then you're going to go stronger, do the second derivative, and it should come out to a number. Alright, another form that we cannot have is an indeterminate when it's 1 to the infinite exponent, or 0 to the 0 power, or infinity to the 0 power right there. So these are the 3 types right there you cannot have. Now when you have something like this, what we're going to do is we're going to do the logarithms. So if you remember from pre-calculus, right, when we have an exponent, we could do the logs on both sides of the equal sign, and that will bring exponents down. So similar to that, we're going to go ln on both sides right there, and once I do the ln, I'm going to work on the right-hand side of that equal sign just like that, using the L'Hopital's right there. We're still doing the derivatives of the L'Hopital's rule right there. After I've completed and substituted all my numbers in there, then from there, we're going to bring the ln over on the other side of the equal sign. So remember from pre-calculus, if you bring ln over, it turns into e, so this is going to be in something e to the something number up here. Okay, so let's try an example then. So example 4 I'm going to have is this right here. If I substitute in 0, 0 to the 0 power, again, we said that does not work. So we're going to have to manipulate this. So we're going to do ln on both sides. When I do ln from the pre-calculus rule, it says that I can bring the exponent down. So this is where it comes down to. And I have this ln x right here. So now I have to work on this side right here. We're going to leave this ln out here until we're done with the problem. Now on this side right here, in order to do L'Hopital's, I need to have a fraction. So we're going to manipulate this problem and make it into a fraction. So this x right here, I can bring it down like this, 1 over x. Because if I do 1 over x right here and I multiply the reciprocal, right, that becomes x over 1, which goes back to this problem right here. So through practice, you're going to find anytime you have an x, just make it into a denominator or fraction down here as 1 over x. Okay? Now, from here, we're going to use our L'Hopital's. So the derivative of ln x is 1 over x. Derivative of 1 over x, we're going to bring that x up as an x to negative 1 exponent, right? Bring it down, subtract 1 on the exponent, so we're going to look something like this right here. Okay? Now, from here, I'm done with my L'Hopital's, so I'm going to do is I'm going to simplify this. So if you simplify this, we're going to multiply the reciprocal of this right here, the negative x to the 2nd power. We're going to multiply to the reciprocal of that with the 1 over x. And then from there, we're going to get negative x. Because if I multiply the reciprocal, the x's should cancel out, at least one of those, right? So that leaves me at negative x. Okay, now I'm done completing with my L'Hopital's and simplifying. Now I need to substitute in 0 here. Now obviously, there's no such thing as a negative 0, so we're just going to have a 0 right there. Okay? From here, once we have a 0, we need to continue and bring this ln over, because that's the only thing that's left to finish the problem up. So if I bring the ln over on the other side of the equal sign, that gets pushed up as an exponent, so we get e to the 0, and e to the 0 becomes 1. So that's your final answer right there. Okay? So we'll have more questions on this, so I'm going to do a classwork video on just this part right here. I don't think I'll do a video for the L'Hopital's first derivative and the second derivative. So expect the indeterminate ones on this one. Alright, let's go ahead and do the classwork now.